We will introduce quotient vector spaces. We have a vector space over a field F and a subspace of V, which is W. Now, using W, we define an equivalence relation on V as follows. Whenever we have two vectors in V, we say that they are related to each other if the difference is in V. And I claim that this is an equivalence relation. So claim is an equivalence relation. On V. Proof. Now, what should we show that this is an so that this is an equivalence relation? Yes, that we have to prove three things. This should be reflexive, transitive, and symmetrical transitive. Reflexive means any vector should be similar to itself. Okay. Let V in V. Then V minus V is just zero vector. And this is, of course, inside the subspace V. Therefore, and V is related to V. So that it is reflexive. Okay. Second, it should be symmetric. Is it symmetric? Well, let's see. Let V1, V2, V, and assume V1 is related to V2. What is the definition of this equivalence relation? Well, these are related if and only if the difference is in W. So, V1 minus V2 is in W. But this is a subspace. So, it is closed under scalar multiplication and addition. I can just multiply this vector with -1 and obtain another vector in the same subspace. Then V2 minus V1, which is just -1 times V1 minus V2, is still in W because W is a subspace and therefore it is closed under scalar multiplication. But this means what? V2 minus V1 is in W. This implies V2 is related to V1. So if V1 is related to V2, then V2 is related to V1. Therefore, it is symmetric. Okay. Now we pass to the third condition of being an equivalence relation. It should be transitive. Okay. Now let V1, V2, V3 be in V, and assume that V1 is related to V2 and V2 is related to V3. Well, this means what? Then V1 is related to V2 means V1 minus V2 is in W, and V2 is related to V3 means V2 minus V3 is in W. So I have two vectors in W, and W is a subspace, therefore it is closed under addition. This means, so V1 minus V2 plus V2 minus V3 is in W because it's a subspace. But what is this summation? This is just V1, V2s are cancelled, right? These are cancelled. So we see that hence V1 minus V3 is in W, and this implies that V1 is related to V3. So what we have seen is the following. Then if V1 is related to V2 and V2 is related to V3, then V1 is related to V3. Therefore, it is transitive. So it's an equivalence relation. Okay. Well, if it is an equivalence relation, then I can talk about equivalence classes, right? The set of equivalence classes of this relation ya da şöyle before I talk about this, what are the equivalence classes? Okay, now for any vector V, the equivalence class of V is what? Is this set. It should be the set of all vectors so that they are related to. Okay, let me denote the equivalence class with this. So what is this? This is the set of all vectors in V so that V minus U is in W, right? But note that that set is the same as this one. Okay. If you let this guy, sorry, V minus U is a vector in W, right? Let me denote it with W. Then we see what? Then we see the following. U is just V plus, no, U nedir? V minus U. V minus W. Şöyle yapayım. Şuna da eksi W diyeyim. W oradaysa eksi W diyeyim orada. Let me call this vector ya da şöyle diyeyim. Şöyle, okay. V minus U is in W. Therefore, U minus V is in W. And let me just call this vector W. That W denote this vector. Then, what is U? U is just V plus W. Okay. So, the equivalence class containing V is nothing but it was U in U so that this difference is W. But instead of U, I can just write this. This is V plus W and W is in. Yani ne demek bu? V vektörünü alıyorsunuz. Ona W'daki her şeyi ekliyorsunuz. Kocaman bir küme elde ediyorsunuz. O küme sizin denklik sınıfınız. So what we do, we have, let's say, our vector space V. Okay. Here I have, for example, what is the equivalence class of 0? Well, it is just 0 plus W, which is just W, and W is in W. So the equivalence class of W, sorry, 0, is just the W itself. So one of the equivalence classes is W. Okay. It is the equivalence class of the equivalence class represented by 0. And then we have equivalence class represented by some vector v1. And then possibly some other vector v2. And so, okay. So these are the other equivalence classes. They partition the whole vector space. This is, of course, not an actual picture. This is just a model for the quotient space. We know that equivalence classes are disjoint sets, right? They have no common elements in an equivalence relation. So they're all disjoint. And this is the equivalence class represented by the 0 vector. And these are the other ones. Actually, here, instead of this, I can just write V1 plus W. Why is that? Because it is V plus all the elements in W. Therefore, I can just write this equivalence class. So we may represent using this. This is like this. This vector added to this subspace, meaning that you are just considering all the elements of this form. V plus W, W is in W. Tamam mı? Yani bu notasyonun amacı nedir? V'yi W'daki bütün vektörlerle toplayın. Tamam mı? Elde ettiğiniz küme sizin denklik sınıfınız. Zero'nun denklik sınıfı, Zero'yu W'daki her şeye ekliyorsunuz. W. Evet, söyleyeceğim. İyi soru. So, this way we have all this equivalence classes. We will consider the subspace of, the set of all equivalence classes. The set of all equivalence classes will be denoted as this notation, V quotient W. So V divided by W. Okay. So what is this? This is the set of all equivalence classes. So I can just write it like this, right? The set of all equivalence classes. But another, or maybe more practical way of writing is this. This equivalence classes is obtained by adding V to all the vectors in W. I can also use this notation. Okay. The title of this section was that the quotient vector space. Well, this is the quotient set, but has no vector space structure yet. So the set of all equivalence classes will be denoted like this. This set, the set V over W of equivalence classes is also called the quotient set. So this is set-wise quotient, okay? Quotient set. Tabii bir consideration'la elde edilmiş şey. But we will show that actually this is a natural vector space structure. In has a maximum like a canonical vector space. Right. How? To show that this is the vector space structure, I have to define vector space operations. What are they? Addition and scalar multiplication. And then we have to show that those operations satisfies all the axioms of being a vector space. So first I have to introduce operations. One of them is the addition. So I have to tell you how to add. So we have to define an addition operation. On this set. Whenever you give me two equivalence classes, I have to obtain another one. And I have to tell you how you obtain them. This operation will not be the addition operation on V, right? It is defined on a different set, but they are related. How? Well, we define it this way. Let's say I take this equals class. Okay. And then I add this. Şunu isterseniz şöyle prime diyeyim ya. This one. Şimdi bu iki denklik sınıfını nasıl toplayalım? Evet. Yani ilk akla gelen şey nedir? Eğer bu doğal bir şeyse temsilcilerini toplayalım, değil mi? To define two equivalence classes, the first thing that comes to our mind is to add their representatives. Representative here, representative here. So let's say, just take this representatives. You get a vector in V, and then look at the equivalence class determined by this representative. Evet. Prime, no, there's no prime here. No. Burada kullanmadım. Prime tek burada var. But you see, adding two equivalence classes actually became just usual addition. You take representatives and add them up. Can I define it this way? It looks very easy, right? So it shouldn't be right. I mean, it is very easy. We have to prove something, right? Ne ispat etmemiz lazım? Well defined, değil mi? Yani siz iki tane topluluğu topluyorsunuz. Toplarken de diyorsunuz ki herhangi bir rastgele temsil çıkarayım, onları toplayayım. Diğerleri itiraz edebilir, değil mi? Diyebilir ki ya onu niye seçtin? Beni seçseydin başka şey çıkacak. Değil mi? O zaman ne göstermek lazım? Temsilciden bağımsız olmalı. Yani iki topluluğu toplayacaksan, yaptığın işlemde temsilcileri kullanıyorsa, o temsilciden bağımsız olması lazım. Başka bir temsilci seçseydim başka şey çıkacak. Ne anladık? Böyle şeyler değil mi? Yani olmaz. Kabul edilebilir bir şey değil. Temsilcileri toplayabilirsin ama o toplulukları toplama anlamına gelmez. Değil mi? Geri kalan itiraz etmemiz lazım. Must show what? This is well defined. Ne demek well defined? If I choose different representatives, I should be able to get the same result. Well, let's say V1 is the representative of this equals class, but this has another representative, maybe. Let's say V1 prime. Okay. V2 is a representative for this class, but it may have another representative. What I must show is the following. If I use this two representatives, I obtain a summation. What if I use this two representatives? I will obtain another equivalence class, I will show that they are the same. So that it doesn't matter which representatives you choose. So must show, need to show the equivalence class obtained by using this representative is the same as the equivalence class obtained using the second representative. And this means what? This is possible. So these two equivalence classes are the same if and only if what? Bunlar aynı denklik sınıfı ne demek bu? Bu denklik sınıfının reprezentatifleri, bunun reprezentatifleri aynı şeyin içinde kalması lazım. So this is if and only V1 plus V2 minus V1 prime plus V2 prime is in W. Değil mi? Bunların birbirine eşit olması için aynı hani konseptler olmaları veya işte aynı denklik sınıfında olmaları ne demek? Bu nesne bu denklik sınıfın içinde, bu da bunun içinde. Bunların aynı olması için bu ikisinin aynı denklik sınıfında olması lazım. Yani ikisinin farkı burada olacak. Ama bu fark neye eşit? Dikkat ederseniz bu şunun aynısı şey değil. V1 eksi V1 prime plus V2 eksi V2 prime. Ama V1, V1 and V1 prime are in the same equivalence class. Therefore, this is in W. This is also in W because they represent the same equivalence class. So this is in W. This is in W. Therefore, the sum is in W. So this is in W. Therefore, this is value 5. Tamam mı? So this is how we define addition. What about scalar multiplication? Well, I guess we can guess how I am going to define scalar multiplication, right? Again, we will just use a representative. For any scalar and an equivalence class, I should obtain scalar product, which is another vector here. So when you give me a lambda and an equivalence class, I should be able to define the product. Nasıl tarif etmeliyim sizce? Değil mi? Yani vektörleri çarpmayı biliyorum. O zaman bu vektörü bununla çarpayım. Onun temsil edici sınıfa bakayım. Yani sınıfı bir sayıyla çarpmak istiyorsanız rastgele bir temsilci seçin. Onu çarpın. Elde ettiğinizin sınıfına bakın. O sınıftaki herkesi çarpmaya eder. Yani lambda b plus w. This is my definition. Is it well defined? Tanımlamak güzel ama bu iyi bir tanım bu. Yani temsilciden bağımsız bu. Bugünkü kavga da ondan değil mi? Ne diyor bir grup öğrenci? Onlar bizi temsil etmiyor diyor. Yani aynı şey. Buradan temsilcilik önemli bir şey. Okay. Let's see if it is verified. So what we have to prove is the following. If V1 plus W is represented by some other vector, then we should show that lambda V1 and lambda V2 represent the same again equals class. Is it true? Well, if these are the same, then of course V1 minus V2 is in W. But W is a subspace. Right? So you see that we are using strongly the fact that W is a subspace, right? Since this is the subspace, then lambda times V1 minus V2 is also in W because it's a subspace. If you have a vector in that subspace, any multiple of that vector is also in that subspace. But this means what? This means that WV1 minus WV2 is in V. But if this difference is in V, then these elements are equivalent, right? They are related. Therefore, they represent the same equivalence class. So this implies lambda V1 plus W is equal to lambda V2 plus W. Therefore, it doesn't matter which representative you choose here. You may use V1 or V2, doesn't matter, you get the same result. So this means, is it verified? This is also yes. Are we done? Well, not really. We have defined two operations, vector space operations, but one has to prove that with these operations, this is really a vector space. So next, we need to show that V over W is a vector space with these operations. What are those operations? I mean, what are those conditions? First of all, with respect to addition, this set should be an abelian group, right? Abelian group means that it should have a zero element. Addition should be commutative and associative, and every element should have an additive inverse. So, first of all, we should prove this. First, this operation prime is an abelian group. And that involves several things. It should have a zero element. What is the zero element here? It is the element represented by the zero vector. So zero element should be just 0 plus W. Well, it is just W. Is it the zero element really? Let's see. So for that to be zero element, whenever I add to this, I should get this element. But how we define our addition? I just take any two representatives. V here is 0 here, okay? V plus 0, and then W. Well, V plus 0 is V because this is the additive identity element of my original vector space. So this is just V plus W. So this element added to this one gives me this. And you can interchange these two and you get the same thing. So this is the identity element. Tamam mı? Bir özellik bu. Sıfır elemanı is the zero. Abelian olmak nasıl gelecek? Commutativity. Well, V1 plus W plus V2 plus W. What is this? This is by definition V1 plus V2 of W, right? I got 8 representatives, but this addition is in V and V is an abelian group. Therefore, this is the same thing as V2 plus V1. And this is again from the definition of our vector addition. This is just V2 plus W plus V1 plus W. So this means this element plus this element is the same as this element plus this element. So I can interchange the two. Şurası prime, evet. Şurası prime. Şurası prime. Ha? V ve W vektör space'ler. Bu V'nin içindeki toplam. O yüzden yani bu V'den bağımsız bir şey değil. Ben V'nin vektör uzayı yapısını kullanıyorum, değil mi? Aslında yaptığım şey, dikkat ederseniz V'nin operasyonlarını kullanıyorum. Yani kafadan operasyonlar uydurmuyorum. V'nin operasyonlarını alıp Quotient uzayda kullanıyorum. Tamam mı? O yüzden bu V'nin Quotient'ı. Yoksa rastgele bir set değil. Set olarak bakacaksanız zaten çok fazla set yok. Neler var? Sonlu kümeler var. Z var. Ondan sonra da continuum hipotezden dolayı bir tek R var. Bir de R'den daha büyükler var. Zaten onlara pek gitmiyoruz. Yani topu 3 tane set var. Yani sonluları bir tane görürseniz Z, bir de R. Ama dünya kadar yapı var. Neden? Çünkü biz nesnelere set olarak bakmıyoruz. Değil mi? Üzerlerinde yapı var. O yüzden hani bu nesne bir set. Ben burada milyon çeşit toplama tarif edebilirim. Ama bu V'nin bir bölüm uzayıysa V'nin operasyonlarını kullanır. Öbür türlü buna bir set olarak bakarsanız bu ya sonlu bir küme, ya Z kadar elemanı var, countable, ya da R kadar var. Ya da daha büyük. Ama hani öyle bakmıyoruz. Değil mi? Üzerlerinde yapı var. O yapıları korusun istiyoruz. Okay. I will not go through all of them, but you know, one can show these operations. Defines a vector space structure. On D over W. Well, we have a canonical map. We have a canonical homomorphism. Let's say 5 from D into the quotient. Nasıl olmalı? Canonical dediğime göre ne demek bu? Yani Turgut'un deyimiyle lafımın maruz görün ama hani böyle işte herkesin aklına gelecek ilk şey olmalı. Canonical dediğiniz şey o. Hani ilk aklınıza gelen şey ve onun çalışması lazım. V'yi burada nereye götürürsünüz? İlk aklınıza gelen nedir? Değil mi? Efendim? Evet, B'yi alacaksınız. B'ye götürüyorsunuz, değil mi? B'nin temsil ettiği sınıfa. İddia nedir? Bu bir canonical homomorphism. Isomorphism mi? Değil. Çünkü birebir değil. Onu biliyoruz. W'nun her şeyini alıp sıfıra götürüyor. Right? Anything in the W goes to W, but W is represented as the zero element here. Right? So what is the kernel of this guy? Okay, now this is a homomorphism. First, we have to prove that. Let's say V1 plus V2. What is this? Well, by definition, this is just V1 plus V2. The class represented by this. But we just defined our addition in the quotient vector space like this. Right? This is just equal to this one, but this is just phi of P1, and this is phi of P2. Okay. Therefore, it preserves addition. What about scalar multiplication? Well, it is just lambda B plus W. But we just saw that this is nothing but this gadget, right? This is just our definition of scalar multiplication. But this is just lambda times phi of B. So this is a homomorphism. Okay, it's a homomorphism. What is the kernel of this? What are the elements which are mapped to 0? Well, 0 is just the equivalence class of the 0 vector, which is the subset W, right? So kernel of phi is what? It is the set of all elements in V such that phi V is just the 0 element of V over W. What is the 0 element of V over W? This is just 0 plus W. In other words, this means that but what is this? This is just V plus W, right? 0 plus W. So it means V is in the subspace spanned by, represented is the, no, V is in the equivalence class represented by the 0 element. So this is the same thing as saying V is in W. Değil mi? V eksi 0 W içinde. Ve tersine de gidebilirsiniz. V buradaysa V bunu sağlar, bunu sağlar, bunu sağlar. Bu ne demek ama öyle V'ler ki W'nin içinde kalsın. Bu W. So kernel phi is just W. Okay? So this is a homomorphism. And this is onto, right? Note that is onto. Because the element, this is just the image of this. So it's on, right? Any element of the quotient vector space has this form, but this is just the image of V. Therefore, phi is onto. Okay. So what we see is the following. We have this homomorphism. It is onto. So the nullity theorem tells us what? Rank nullity theorem tells us the following. Dimension of B is, if they are finite dimensional, of course, dimension of kernel plus rank of V, rank of phi, veya dimension of image. Öyle yazabilirim. Dimension of image kernel V, kernel phi, image phi. Kernel phi is just W. Therefore, this is dimension W. And this is dimension of image. Image is what? V over W. So what is the conclusion then? So dimension of the quotient space is just dimension of V minus dimension of W. Of course, for this to be meaningful, this number should be finite. If this is finite, of course, this is finite because it's a subspace. But otherwise, this equation doesn't make sense. Provided that dimension is fine. Şu var ama we have many quotient spaces when this and this one, both of them are infinite dimensional, but the quotient is finite dimensional. And they are very important, especially in geometry and topology. Okay, they are using this kind of stuff a lot, and they represent very geometric objects. Okay, we have infinite dimensional vector spaces, infinite dimensional subspaces. Both of them are huge, but the quotient is very low. Finite dimensional, and it has a lot of about the geometry. What's going on? Okay. İyi. Ne zaman görüşecektik? Bana e-mail atın. Ben unuturum. Tamam mı? Bana